So I put a little video about one of my favorite science fiction shows, Star Trek, on there about warp drive, and there's a good reason for that. And that's because what I'd like to think about for a second is an interesting problem, right? So let's assume the top speed of an auto in 1957, which is that's about when um, and that's about when Moore began his observations about the fact that the number of transistors doubles every 1.5 years or so. So let's just say it doubles every 2 years. Oh, actually, no. Well, let's say it's every 1.5 years. Okay. So let's assume the top speed of an auto in 1957 was 50 miles per hour. Okay. And let's assume that the same kind of phenomenon applied to the top speed of an automobile. So instead of like the top speed of a CPU, because remember the density of transistors, as they get more dense, the speed of the CPU increases. So we're saying let's assume we have an auto instead, and Moore's law applied to an auto instead of a CPU. Just to give you some idea of how much faster CPUs are, let's think about speeding up an auto according to Moore's law. All right. So the question then is, if Moore's law applies to the auto, how fast is it in 2020? Okay. So that's the question that we want to answer. All right. So we can do some work to try to figure that out. And what I like about this problem is, right, I haven't really given you any information to lead up to this problem other than the idea about exponential growth and a sort of discussion of Moore's law. This is a really nice kind of problem where you have to sit and think about it a little bit and see if you can figure it out. So what I would like you to do is work on this a little bit and see if you can figure it out. So right there in your notes, just hit pause and see if you can figure out the answer. And then when you're done and when you've worked it out, either you've gotten frustrated, you're not sure where to go, or you haven't gotten frustrated and you've got an answer, then you can just hit unpause and you can compare your answer to my answer. Okay? All right, so hit pause now and work on it. Hit pause. Go ahead and hit it. Okay, so I'm assuming you unpaused it and now you're either frustrated because you couldn't figure it out or you have an answer and you're feeling pretty good. So let's try to work this out. So the first thing we want to do is we want to figure out the big picture is we need to figure out how many times the auto speed is going to double between 1957 and now, right? So the first thing we're going to do is we're going to take 2020 and subtract 1957 from that. And what does that equal? Whenever I'm doing lectures and stuff like that, I get a little bit of performance anxiety. So sometimes it's hard to do stuff in my head. I'm sure you feel the same thing. If a professor calls on you and you're like, I knew it. If you didn't call me, I would have known the answer. So I'm just going to use my calculator just to make sure I don't make a mistake. So 2020 minus 1957 equals 63. So there's 63 years between 2020 and 1957. All right, so now the question is, how many doublings how many times do we double the speed? in 63 years? So that's the next question we have to answer. And so to answer that, what we have to do is say, well, according to Moore's law, what's the rate of doubling? And Moore said anywhere between 1.5 and 2 years. So let's say it's 1.5 years. So things happen really fast. So how many doublings are we going to have? Well, we have one doubling every 1.5 years. And we're going to multiply that by 63 years. And that should give us the number of doubling. So effectively, we're dividing 63 by 1.5, which should make sense. Okay, I'm being careful about the units now because I find that you get to the answer to a problem when you use units. When the units cross out and you end up with the unit type that you want, it means you probably did the problem the right way. So 63 divided by 1.5, that's going to give us 42. What a lovely number. So 42 doublings. So we're going to double 42 times. So how do we find out what 42 doublings is? That's an interesting question. Well, one thing is we could take 63 and go on a calculator and double it 42 times. That's a lot of doubling, and it's probably kind of easy to make a mistake on your calculator. Another way you can do it, though, is we can say, we can take the number 2 and we can double it a certain number of times. So we know we're going to double it 42 times. So we're going to take the number 2 and double it 42 times. That's going to give us the multiplier that we're going to use to get us that's going to tell us how many times we're going to have to multiply that 50 miles per hour to get to our answer. So 2 to the 42 times, or just 2 to the 42. So this is going to give us the total multiplier that we're going to have. So I see my calculator here is not scientific. Maybe I can get it to be scientific. There we go. All right, so 2 to the 42 equals, whew, that's pretty big. Let's see, let's see if I can get that in scientific notation here, because that is just one big number. Okay, well, I'll just count it. So let's see, that's million, billion, trillion. So it's 4.4 times 10 to the 3, 6, 9, 12, 13, 10 to the 13th. Ooh, that's a big 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah, 4.4 times 10 to the 13th. So quite large. We're into the trillions here. So 4.4 trillion times. That's how many. That's the multiplier that we're going to use to multiply by our 50 miles per hour. All right, so we're going to multiply that by 50 miles per hour. And that's going to give us about, let's say, 200 times 10 to the 13th miles per hour. So that's pretty darn fast, right? And that should give you some idea of how, I mean, I'm still not quite done with this yet. I'm thinking, miles per hour. I mean, what about the speed of light, right? So if we were to figure out how many times the speed of light this is, maybe that would be helpful. So if we have 200 times 10 to the 13th miles per hour, and the question is, how many times the speed of light is that? Well, if we were to divide that by the number of miles per second, that's speed of light, but get that into hours. So divide that by 186,000 miles per second, but we got to get that converted to hours, times 60 seconds per minute, times 60 minutes per hour. So if we do this, that's going to give us the number of times the speed of light. Okay, these units are going to cross off. Oh, the hour's going to stay there, and that it's going to stay there. So that we'll end up with the same units on the top and the bottom, and we'll end up with the number of times we get speed of light. Okay, so I was able to wrestle my calculator into submission. So taking this 200 times 10 to the 13th and dividing it by the speed of light converted to miles per hour, we end up with approximately 300,000 times the speed of light. So just imagine that, right? If we could apply Moore's law in terms of automobile speed and move from 1957 to now, we would have an automobile that if we put on the gas would move 300,000 times the speed of light. That's pretty darn remarkable. Now, just you know, for a little bit of nerd satisfaction here, I'm curious about what warp factor that would be. So I think that the early versions of the Enterprise, Star Trek Enterprise, couldn't go much past like warp factor 2 or 3 or something like that. So to get the warp factor, you take the cube root of the number of times the speed of light. So if we take the cube root of this number, we end up with warp factor and the cube root of 300,000. That's going to come out to be warp factor 66. Warp factor 66. So that's pretty darn fast, scarily fast. Probably go back in time or something like that if you were able to do that. All right. So in the world of Star Trek, not in the real world. Okay. So that ends our discussion of the CPU, and we're going to move on to something else in just a second.